have a constant ratio from any term to the previous term. So that means what you do to check that is you do, here's this term and here's its previous term. So you do 6 divided by 2, which is 3. Okay? And then let's try it again. Let's do 18 divided by 6, which is also 3, correct? And then if you just keep going, you're going to notice that it's going to always be what number? 3. So that tells me that it has a constant ratio from any term to its previous term. So that's geometric. Okay? So let's try this one. 7 divided by 2 is 3.5. 12 divided by 7 is 1.7. Uh-oh, got a problem. So that doesn't work, does it? It's not geometric, but what is it? Look at it.
The other one.
Which is what?
Arithmetic.
Arithmetic. Because you're adding a 5 every time. But it's not geometric, so no. Okay? So if you have to come up with a function or the rule, this also has a nice little equation. And you will be given this on the test. That's, yeah, you will. In order to write the rule, you need to know A1 and R. Those are the two things you need to know in order to write the rule. Write a rule for the nth term of the sequence, then find A of 6. Okay, so we need to know A1. Do we know A1 here? What number is it? 3. Do we know R yet? No, but we can find out. We can do 12 divided by 3, which equals 4. 48 divided by 12 equals 4. So it looks like my R is going to be what? 4. And my A1 is 3. That's my A1 right there. So now I can just go ahead and plug it into here and come up with the rule. So it's going to be A of n equals A1, which is 3, times 4, parentheses or not, it doesn't really matter, raised to the n minus 1. And then you could plug in any n and get that term. That's the rule. Nice, huh?
What is n again?
N is like, remember yesterday when you would, I don't know the name for it, but it's like the input. I would say it's like the input, remember? Okay? Okay, let's try this one. So if we got to write the rule, we're going to have to first find out the ratio, which is going to be negative 12 divided by 36, which is negative 1/3. It's the same if you do 4 divided by negative 12, it's negative 1/3. And if you did the last one, you would find out it's also negative 1/3. So my R is negative 1/3. This is my A1 here, 36. Okay, so now I can write the rule. So I have A of n equals 36 times negative 1/3 n minus 1. So geometric rules are going to have what in them? They're always exponential. So what do you think their graph's going to look like? It's kind of a curve, right? Okay. Will it go down ever? I don't know. That's a good question. We'll have to find that out. Most of the ones I've seen, I'll go up. So, all right. So let's just practice that little graphing thing real quick. One term of a geometric sequence is A5 equals 54. The common ratio is R equals 3. Write a rule for the nth term. Well, they gave us R, but I don't have what? I don't have the first term, A1. So I got to figure that out. Here's the rule, general rule. I'm going to plug in what I know. I know this is 54. I don't know A1. I know my ratio is 3. Put that in parentheses. And I know my n is what number? 5. So I'm going to do 5 minus 1. So I plugged in what I do know. Yeah.
I thought 54 is 85.
It is. It's my output. And the 5 is the input. Okay? So then if you just do the math here, you're going to figure out what a to the 1 is. Or A1 is. 3 to the 4th times 3 to the 4th which is 81. Divide both sides by 81. It's kind of ugly, but it turns out to be pretty. 54 over 81 equals 2/3 when you reduce it. So I know my A1, my first term. I can plug it in now to the rule. I have that, and I can write my rule. So it's going to be a to the n, or an equals, up here, yep, you start with A1, which is 2/3 times 3 to the n minus 1. See where I got that from? There's my rule. I found out what A1 is. I was given R, so I could write the rule. Okay, now, just if you go to the calculator and you pick some points, look, they're in the positive x values here. So I just went to my calculator. Actually, I should write it like this, n and a of n. It's 1, 2, 3, 5. I jumped and I got those points. And it's 2/3, 2, 6, and 54. Off the calculator. I just went to the calculator, but it's pretty easy to do it in your head here too. But now plot those. Make this 1, 2, 3, 4, and 5, and see what it looks like. Yeah, the first one's going to be really close to the x-axis. Look at that nice exponential curve. Isn't that beautiful?
Your idea is beautiful.
And fun? Beautiful and fun. Okay, that's the first page. No, they're not really. This is very, very similar to what you did yesterday with elimination. You had to find A1 and you had to find D. Okay? This is going to be very similar. Stay with me. Two terms of a geometric sequence are A3 equals 45 and A5 equals 405. Find a rule for the nth term. Well, in order to write the rule, I need R and A of 1. And remember, this is the notation or the form that we're looking for. Okay, so it's very similar to yesterday. The first thing you do is you write down what you know. So if I look at this first one here, I know that A of n is 45. Don't write too big either. Okay? I don't know A of 1. I don't know R, but I'm just going to do this in one fatal swoop. I know n is 3, correct? 3 minus 1 is 2, so it's going to be r squared. You see how I got r squared?
Wait, no.
N is 3, right?
N is 3.
So I did 3
Okay,
minus
got it.
1. Okay? And then I'm going to write the second one. 405 equals A of 1 times R. What's the exponent's going to be 5 minus 1, which is 4. So that's what I know so far. Okay. I'm going to take and I'm going to rewrite this and I'm going to solve for A1. So it's going to look like this. That's all I can do, right? I'm just rewriting it and getting A1 by itself. This is not elimination. This is going to be substitution for this one. So do you all see how I got that? Okay, so now I'm saying, all right, so I have A of 1 by itself. So can I take this and plug it into this equation for A1? I sure as heck can. And see, let's like, it's called let's just write this down. I'm going to say using substitution. So I'm going to rewrite that over here. It's going to look like this. 405 equals 45 over r squared times r to the fourth. Oh, look at that. Now we can figure out what r is. Isn't that cool? Now look. This is really in the numerator, isn't it? It's really over 1. So I really have r to the fourth divided by r squared. Correct? So this goes away, and I have 2 left here. Do you see what I did? R to the fourth is in the numerator, so it's really r to the fourth divided by r squared. So I can get rid of that denominator and have 2 left in top, r squared in top. So now it looks like this. 405 equals 45 r squared. And divide both sides by 45. R squared equals 9. And r, let's just use positive. Let's just think about, yes, it is plus or minus, but r equals 3. How's that help me? Plug it in where? Right over here is where I would probably put it. So you don't have to wait for me. Did anybody do it? A of 1 equals 45 over 3 squared. What you going to get for A1? A1 equals 5. So 3 steps, basically using substitution. So now I can write the rule. It's A of n equals A1 is 5. The ratio is 3 to n minus 1. And I wrote the rule. Okay, I'm going to ask you to just make sure you absorb what I did here. Is this good? Because I'm only doing one example like that. Could you do it? It's not too bad. Not too bad. Okay, let's do summing of geometric series. Here we go. N represents, again, the number of terms. Yes? Hey, can I just... All right, find the sum of the geometric series. So, it's a little bit different than the other one, but you can still, it's very workable. So, I can see, remember this. Remember that A of n equals A1 times r, n minus 1. So in this function right here, what part of it is r? 3 over 2. If you look at this, right, the r is 3 over 2. So that's my r. What's A1? 4. Okay? So you kind of have to know what that is, just to kind of help you set this up. So how many terms do I have? 6. So it's going to be S of 6 equals, if I sum up all of the first 6 terms, A1 I decided was 4. And then you do 1 minus the ratio, R, which is 3 halves, to N, which is the number of terms, which we decided was how many? 6. Because that's what this number is right here. And then you do 1 minus R. And that's how you set it up. And then you kind of just do the math, which is a little bit ugly for this one. If you just go to your calculator, it's sort of like this. I rounded a little bit, so it's not actually accurate. The book wanted us to leave it in fractions, but that's really ugly. So I just kind of did it in decimals. I want to know that you can work with this rather than you can work with fractions. So if you round a little bit, that's okay. All right? All right, in 1999, we're going to do a quick story problem. It's not that bad. 586,000 used cars were sold in Maryland. From 99 through 2004, the number of used cars sold increased by 3.8% per year. So my multiplier, since we're working with exponents, my multiplier this time is going to be 100% of the cars oops, 100% plus 3.8%. The thing that I'm going to multiply by every year to find out how much it increases is 103.8%. That is my ratio, or my R, that I'm multiplying by. Yes? This is 100%. I know it's ugly, sorry. 100%. So this is going to be my R. Every year, if I multiply by 103.8%, I can guess how many cars I'm going to have to sell the next year. All right, so write a rule for the total number of used cars sold, A of n, in thousands, in terms of the year. Let n equal 1 and represent 1999. So remember, my rule form is A of n equals A of 1, stop. What's my starting value? It's just like a graph. It is. A of 1, my first one, is 586. And my multiplier, or my R, is 1.038. And then I write n minus 1. That was easy. What's the total number of used cars sold in Maryland from 1999 to 2004? Well, if 99 is 1, 2000, 01, 02, 03, 04. So there's 6 of them, correct? It seems weird because you want to say it's 5, but it's really 6. So n is equal to 6. So you just do the summation. S is 6 equals A1. I'm using this formula right here, the summation formula. 1 minus my multiplier, which is 1.038, my R, to the n, which is 6, all divided by 1 minus 1.038, using that summation equation. It's about 586 times 6.6, which gives me 3868 approximately, but don't forget we're talking thousands in thousands, so it's actually going to be 3868, that many cars. Not too bad, huh? It's okay. If you think about ratio means what you're multiplying by every time. So here's your homework. Or practice, I should say. Page 814, 3 through 51, every other odd, and 57.
What?